So everyone, I mean, this is open to everyone. So if somebody has some problems that he wants to suggest or whatever, feel free to raise your hand, go to the board. So I think that Keith has some problems that he wants to share with us first. So maybe you could start, and then other people can. Yeah, this is recorded.
I give my permission. It'll be worth it if one of you solves one of these problems. Otherwise, I may withdraw. So the idea of these questions is to take classical theorems and relax the conditions under which they hold. So theorem 1 is, I will put the E for Eberhard-Hopf, distinguishing from Heinz-Hopf. So this theorem says that geodesic flow C infinity surface is ergodic. And just to be clear, this is with respect to Leopold metric. Theorem 2 is. I've posted a hypothesis with negative curvature. So this can be variable. So this is really the problem that the Hopf argument was created to solve. And then theorem 2 is the diffeomorphism version of Nosov's extension of this to higher dimensions. So Nosov, a C2 volume preserving diffeomorphism of a compact manifold is ergodic, obviously with respect to the volume. So those are the classical theorems. And here are 3 possible improvements to these theorems, none of which have actually been made yet. So number 1. So in theorem 2, could we take C2 and weaken it to C1? This is a question that Charles Pugh has been thinking about since maybe 1970. One of the difficulties with this is if the answer is, I think the expected answer is no, but nobody's come up with a counter-example to establish that it should be no. If you want the answer to be yes, you are not going to be able to copy Nosov's proof. There's a paper by Robinson and Young from about 1980, which says that the foliations, the stable and unstable foliations, may be non-absolutely continuous. So in this example, the non-absolute continuity happens sort of zero volume, affects zero volume. But this gives you something to think about. So number 2 is, so I think in either of them, in 1 or 2, can we take compact and change that to finite volume? So you can do this easily if you keep the kind of estimates that compactness would give you. It's easier to sort of explain what I want to say in the geometric setting. So think of a torus with a puncture, put a metric of negative curvature on it. I'm happy for you to make the curvature of this metric as close to -1 as you want, as long as you don't make it exactly -1, because that's too easy. but no control over the derivative of the curvature. So somewhere way out on the cusp, the derivative of the curvature could be huge. Further out, it could be huge. You're going to have trouble running the usual proof. As an example, since we don't have a lot of time, I will just say that the three authors have names beginning with B. Well, Baumann and Brian. And I'm the third, Baumann and Brian, I'm the third B. And in this paper there's an example, in fact, of a cusp on a torus with the curvature is pinched as good as you want. When you look at the way that the stable and unstable foliations vary, it is not held a continuous. You can make the modulus of continuity as bad as you wish. Misha Brin was very insistent on creating this example. And I think he's been thinking about this question probably since about 1970. Perhaps he's found other things to do recently. Anyway, and then number 3 is, so it's number 1, let's try to change negative to non-positive. Okay, that desired improvement was a theorem in the middle of the 1980s, until it was realised that the final step in the argument was wrong. I mean, the result might still be true. The argument that was given then is undoubtedly wrong. And so there is a set which is called the singular set, and this is the set of unit vectors. Gamma V is the geodesic defined by the vector. K is the Gaussian curvature. You want this to be 0 for all t. So absolutely everywhere along this singular geodesic, you see 0 curvature. You look at the set of vectors tangent to such geodesics, and the question is, does Sing have measure 0? So on the complement of the singular set, which amazingly is known as the regular set, it is known that you have ergodicity and other nice things like mixing. And the problem that's left is to settle what the measure of the singular set is. So those are the 3 questions.
For the measure of maximal entropy, it's already known by work.
Yeah, that is actually easier to work with.
Because the measure does not see the singular set.
It does not, and when it provably does not. It is just hoped that this one, the level measure, does not see the singular set. And so I could point out that in the case of surfaces, the only known examples of singular geodesics are closed geodesics. So I've been asking for about 30 years, can you exhibit a non-closed singular geodesic? Nobody's done that. But I was thinking that with some of these questions, there are young people with new methods, micro-local people who really, I think, do have genuine new insights. And maybe with some of these questions, these new methods could lead to something that was not possible before. So I think that's more or less the problems I wanted to present. Any answers?
Any questions?
Right, well, I'm here till the end of the week. I look forward to your solutions.
So anyone else? Anyone wants to suggest some problems? Or I think Johan, you had some problems that you wanted to say this morning.
Micro-local analysis and related field, but So maybe let me begin with not my question directly, but another question. So it's the following question. So this question is well known to dynamical system, people studying dynamical system. So it's the following. So given, I mean, just say, right, on the co-sphere bound of some surface. And the question is that is G1 stably transitive? And I say in diffeomorphism group operation. This stably transitive means that even after perturbation, you can find a dense orbit for the map. So see, this is a map. This is not a flow. So this question is still open, and you can find it, for instance, in Wilkinson, Emmy Wilkinson's ICM report. There's also another question. And this is, I think it's Hollis and Pugh from 75. So I ask that, can one approximate time-wide map, the time-wide map of a topologically mixing also flow by axiom A diffeomorphisms. So if it is not topological mixing, it's just a constant function thing, then you can approximate it. There will be a attractor and the other one is a repeller, and it is not going to be stably transitive. Okay, so these two questions. And then, so there is some progress on these questions. So, so there are some constructions that to show that you can indeed approximate in C1 topology. Before that, there's some C0 topology approximation by Bonatti, Nancy Guillman. I don't know that name because I don't remember how to spell it. And C1, there's in some very special manifold, one can construct example by Ishii, a student of Bonatti. And for this, it's kind of widely open, and nobody have any answer yet. So, like, I know that there's a very precise analytical statement that implies a positive answer to the first. At the same time, when you have negative answer to the second, I mean, for this expression. It's the following. I can even give the proof here. So it's the following. So, and it is kind of related to what I wanted to say during my talk. It's like when you have a dense set of mixing, it doesn't tell you much, but one is more interested in the stable, or maybe let me say, say, uniformly excited mixing. So what does it mean? So if you have some map F, then let's say we have it on some volume preserving manifold. Let me write X. And assume that f satisfies the following property. So there exists the open neighborhood of f, which is open, and also there exists some epsilon bigger than color bigger than 0, such that for any g, no, maybe f tilde inside of this neighborhood, for any a, b, maybe smooth functions, you know that you take this a, and you have this f tilde n times b, and then you integrate it along against the volume, and you minus let me see. I may be wrong, but feel free to correct me if I made something wrong. This is the mu. This is an invariant measure. This is the F invariant probability measure. Okay, so you want this to smaller than something. Latitude depends on a lot of things, but in the end, the speed needs to be
You don't take UF to be the volume?
one is volume, one is not volume. Because after perturbation, it's like you push forward the volume.
You don't keep the property of being volume preserving?
No, you don't keep. That is the point. Because if you study volume preserving, then this is known by AC result and
This is the stable ergodicity theory.
Yeah. If it is a volume preserving, then
That's only Wilkinson.
yeah. And you.
It's still there,
There's no.
Besides, it's mixing, exponential mixing rate, which is stable.
No, this is not. This is the volume, and we wanted to convert to that.
Yeah, but I mean, if you stay within the class of volume preserving because of diffeomorphisms, then it's clear that it's uniformly.
Yeah. But you want to ask about this. This question is hard because you don't preserve whether or not you have this. Let me explain why this implies a positive answer here. Okay, I'm not going to finish. The reason is very simple. It's just that if you just take any, in fact, there should be one of them is volume, one of them is mu. But anyway, you just take these. This would be a consequence of a spectral gap in some space. Once you have this, you will have this, and the transfer burden need to be defined to be adapted to the reference measure, which is that. So I just want to say this is just a uniform spectral gap. So even if the formulation is not correct, you find the correct formulation value. Okay, so why this implies the positive answer to the first? Is because that take any function positive, then let's see, we want to compute this and we take a equals to 1. And what does it mean? It means that b volume minus b, this is O minus alpha. But you can write this as integral of b and volume, I don't know, maybe divided by determinant of f tilde n or something. I don't get this correctly usually. Anyway, so this is at least e to the power minus n epsilon. This. Well, epsilon is the C1 distance between f and f tilde. So it will mean that any measure with this property must be full support. If any B, we have this, then it means that it will be full support. Then it means that F tilde is non-wandering. Right? And Casey, I think Casey knows how to conclude. So once this is non-wandering, it is known that in this case, this map F is robustly, stably accessible. There's a notion called stable accessibility. Anyway, you will hold in that case. So all two things together ambiguity. So it's like if you have this analytical statement, you can prove some purely topological, which is open for many years. And also, if you know this, then this, the answer for this is also I mean, for all the fluid you can prove. And also, in fact, you can also prove for all the perturbation you have a unique SLB measure. The Bayesian is the whole manifold. The Bayesian is the full measure set. So it's like, but to get this, it's very simple, it seems. So I mean, in this case, even among unanswered flows, like we don't know how to do it. Among unanswered flows, let's say in dimension 3, we know that after perturbation it is exponential mixing, but the speed may not be uniform. We don't know how to prove. But like to run this argument, let's see, you at least to know whether uniform this in to get it for different mobility maybe probably more. I hope somebody has some ideas.
Start with a metric of constant curvature, it doesn't change anything, like the problem is the same? Or
What?
if you start with a metric of constant
This part is very general. And also the part about accessibility, because we are starting with the flow, right? Then this is also known. I mean, at least for generic case, this is known. You will have accessibility, then not only on surface and on any higher dimensional flow, you can run this argument as long as you can prove expansion mix, the uniform expansion mix. But I hope that there are some people who have tools to understand it, because after perturbation, the stable leaf and unstable leaf, they are just C alpha. There will be some alpha close to 1, but it will be strictly smaller than 1.
Could I just make a comment about the first question? That this time one map of the geodesic flow is kind of one of the favourite examples of stable ergodicity. So there are two very rather similar concepts, stable ergodicity and robust transitivity. And as far as I know, there's a tendency to have examples which has one property, but it's not known whether the other one has it. And so you can ask the sort of converse question, take a suitable example of something that's robustly transitive and ask whether it's stably ergodic. So there's a general question about the sort of comparison between these two concepts.
That's all for my question.
Thank you.
Well, so 2, 1, 1, 1.
Anyone else?
Yeah, so I came across one question which I was very surprised that nothing seems to be known about it. So if you take a discrete subgroup and a hyperbolic surface, and if you are, so now I'm interested really in the L2 spectrum of the Laplacian, yeah? So no resonances today. Then, for example, if if gamma is as a 2z, then you have a continuous spectrum here, and the mass cusp forms as embedded eigenvalues. And then there's a very old result by Peterson for gamma geometric finite, that if the volume is infinite, then no eigenvalues. And well, the point is, if gamma is geometrically finite, then this is equivalent to that there is at least one funnel, or in other words, also that the limit set of gamma is not the whole boundary. Yeah, and my PhD student Nassim was working on this question in higher rank, and he managed to generalize this result, but he, as a condition, he has something which is not volume, but which is rather a generalization of this condition here. And then, of course, people were asking, but why can't you do it for infinite volume? And we asked, wait, I mean, what happens for SL2 if we remove geometrically finite? Because then, well, if you look at Peterson, he proves more or less he uses this condition. Yeah, it just states it this way. But then you don't have this equivalence anymore, yeah? So you could have infinite volume hyperbolic surfaces with with full limit set. Yeah? And the question is, what is known about the embedded eigenvalues? And we were sure when we were sure that we just have to look up, and the answer is either yes or no. Either there's a counterexample or it's proven. But it seems nobody knows anything.
Remove the condition to be geometrically finite?
Yes, geometrically finite and infinite volume. So if you have this condition, the proof of Peterson works. Yeah. And the problem in higher rank is you don't have geometrically finite. So there is nothing, there is no notion like this. Yeah? That's not it seems, if you look at papers of Kapovic, he says it's the most difficult thing in higher rank that we don't know what geometrically finite means. And so in some sense, the proof of Peterson uses this. So if you have this, even without geometrically finite, it does not, if you look at the proof, it does not need geometrically finite. Yeah? If you have this, you are done. But if you have infinite volume, it seems, so we asked many people, and we even wrote Zanak, and he said, no, he knows nothing about this. And I don't know, I mean, for me, I mean, so if you consider the standard example of such a surface, which is kind of this infinite chain of tori, yeah, in some sense it resembles a chain of atoms, yeah, physically. And I mean, we know in physics that, I mean, if it's periodic, then there's only continuous spectrum, but if we add a perturbation, which means make one of these smaller or not, yeah, then then in physics we can create, or in mathematical physics, we can create localized states, yeah? And I'm wondering whether not someone who knows about kind of how this works, yeah, to create locally states with disorder or with defects, yeah, could not make an argument like this work.
Take a waveguide, if you take a waveguide and you bend it a bit, you can create a localized bound state.
Yeah.
Euclidean waveguide.
Yeah. Well, okay. I mean, you want to do it in the above 1/4, yeah. I mean, of course, there can be discrete spectrum, yeah. I mean, below 1/4. Yeah. But above 1/4, and
you get what you want. So you want to move, you want to perturb one of the tori a little bit to get what?
Yeah, an eigenvalue below, an eigenvalue larger than 1/4. It's quite surprising to me that this seems completely open.
The comment about the waveguide was I don't think it was developed.
But I mean, if you think of Anderson localization, I think it's precisely what people do. Yeah, I mean, they have continuous spectrum, and then they create some.
No, but they don't create only one little perturbation.
No, but okay, you could also think of maybe make this order on the, I mean,
There's no more.
Yeah, but if you create this order on the entire torus, I mean, you probably will get some localized states at the, I mean, that would be the classical Anderson result. You would probably get localized state just at the edge of your so just slightly above 1/4.
but this would be fine. I mean, this is not known, yeah?
Really? There's a book by Veselic, I think, Ivan Veselic, who treats Veselic.
For hyperbolic surface?
No, but just for general Schrödinger type operators and manifolds.
Yeah.
So maybe look at this.
And I'm not an expert in Anderson localization. I mean,
No, but I mean, he looks at two models. So either you add to the Laplacian like a random type potential, which you could express in your surface, or at small metric perturbations. I think so. Maybe this is what you.
So I think my feeling is that this should be doable, a doable question. Yeah? And I was very surprised that nothing is known, and I would be happy to know what's true or not. Yeah?
Okay, thank you very much. So Yannick is saying.
Question of Jan Choubet.
He's too shy to come to the board.
So I have a surface and no soft surface.
So you mean that the geodesic flow is another from the unit tangent model?
It's negative curvature for. And let's assume that the resonances are on lines, periodic lines. Then is it a hyperbolic surface? Because if it's a hyperbolic surface, then certainly it's the case.
Wait, what? So you're just giving yourself points on periodic lines, and you want to.
So that's the real political resonances of the flow. They live on lines.
That's the equivalent analogous of can you the shape of the drums, which has been going around for some time.
So you give yourself the points, and you have nothing more, and you ask, can I create them from an?
No. I assume I have my surface, and this is the resonance of the surface. And I wonder, is it a hyperbolic surface?
You have a. Yeah. No. I got this. I was wondering if he's
Well,
giving
it's
himself just some set of points and nothing more, and trying to create everything from it.
It's a question someone has, come up before, but it's not very.
It's a complicated. So you want the comment on that? It's a very difficult question because you're actually trying you're trying to reconstruct the geometry.
No, I believe that it's a difficult question. I mean, there is no doubt.
Okay, then I have another question that's not from Jan. If you have a flow which is not contact, but it's preserving a one form. So contact would be d alpha is maximum rank. And instead of this, I assumed it's constant rank. Do you have some kind of structure in the resonances? I mean, is there an interesting thing to say about this? That's the thing. It's like a very open question. What can you say about this thing?
So what do you assume about alpha?
Well, assume it's smooth so that you can do something. Because at least C1.
But in dimension 3 is clear, right? has to be contact.
Okay, and yeah, right. So in dimension bigger than 3, because in 3 dimensions, so what happens in 3 dimensions is that if in that case it's maximal rank, so it's contact. And the sub question is if this alpha that I define is smooth, actually does d alpha have constant rank?
So there might be ways of answering that, right? I mean, let's say you go to dimension 5, right? Or maybe to what we're going to say, you have an invariant object, and if it doesn't have maximum rank, there's some kind of degeneracy somewhere which is invariant under the flow. So this creates some sub-bundles that might give you obstructions.
Yes, yes. So the kernel of d alpha is an invariant subbundle.
That's
So
right.
basically, it's you have a subbundle in which d alpha is 0, and transversely, d alpha is symplectic.
That's right. But for example, if you are in dimension 3 for the geodesic flow, that appeared to tell you that you're going to have x, which is in the kernel. So then you have another direction that will project onto the 2 spheres, the vertical 2 spheres, maybe as some kind of a non-trivial vector field. That cannot happen. These kind of arguments, these are very common arguments when you're trying to show, go back to Katok and Ferris, I think, trying to show when the foliations are regular enough, you have some invariant objects coming up. So I'm not saying, I'm not getting an answer, but there's kind of an obvious thing to try.
Well, in general, the kernel of alpha intersected with the kernel of d alpha is a subbundle of EU plus ES, and it's a smooth subbundle. And inside EU plus ES, transversely to this new subbundle, you have a symplectic structure. That's what happens. But
There is no natural orthogonal which should be preserved by the
no, if you have a natural orthogonal that's preserved, then probably you're a fiber bundle. What happens is that you have a contact flow, and you have an extension with compact fibers, and then you will have a contact flow, and upstairs you have the return maps are just Anosov diffeomorphisms of your fiber. To provide you an example, it would be the only example that I understand is the geodesic flow of the modular curve. So it's PSL2R over PSL2Z, and over every closed geodesic you put a torus and then a cat map to come back.
Let me ask you a much simpler question. Maybe you just take a hyperbolic 3 manifold. Do you know how to answer the question?
Hyperbolic 3 manifold?
Yeah, so if you have such a form, can that happen?
No.
Then I don't understand the question. So then you know in that case.
I think the
A hyperbolic 3 manifold will give you a 5-dimensional contact flow.
Yes.
You know the answer in that case, I guess. That's the question. It's a sub-question of your question.
but you take a one form.
Instead of working, many works have been done on contact and also flow. So instead of working with a contact and also flow, replace contact by this constant rank, but not maximal rank.
What you are suggesting is take X to be the geodesic flow on the hyperbolic 3 manifold, and alpha just a one form,
Yeah.
which is invariant by this geodesic flow, and with that property. You answer it.
Does it have to be the contact one?
Sorry.
Doesn't that determine
This defines
It has to be, yeah. So it has to be because it's the only thing that...
Sorry, yeah,
Okay,
sorry,
sorry, I think I understand now.
yes.
Can you exhibit examples of this setup with constant but not full rank?
Yes. So the only one that they can actually exhibit is not compact. But there exists example, and I hope you believe me just on face value.
What do you mean, and also if it's not compact?
Paramétrisation. Then you change alpha. Does it automatically satisfy the alpha maximum rank?
Saying you have the geodesic flow of the modular curve, this part, and then above each periodic orbit you add a torus, and the return map is the cat map.
We're just on periodic orbits.
The torus everywhere.
Explain the dynamics. So it's a torus bundle.
Of PSL to
It's a torus bundle over the unit tangent bundle of the modular curve.
This is very particular because this is an extension.
Yes, it's an extension, yes. I don't know any example which is not an extension. So,
In this case, you can compute the spectrum. Or,
So what you say that
I haven't
here
tried.
your alpha, here alpha is the contact form of PSL2R.
yes, extended by 0 on the fibers. So there's a theorem that says that if you have an example like this, which is homogeneous, then it's an extension that looks like this, but with higher dimensional things, possibly. And to have compact examples, you need dimension 7. And it's a question, the problem is they all look like this, and you have a geodesic flow of constant curvature. So that would be some G over K, and G needs to act on something, which is a vector space, and you have to have a lattice in G that preserves a lattice on your vector space, and that's like number theory. So to build them, you need, it's an arithmetic example, so that's why I can't really explain the construction. Because
maybe you could say there's something in dimension 5, right? Like there's
well, this one has dimension 5.
No, but there's a result by.
Oh, yes, okay, so yeah, the reason why I'm interested in this is because I'm interested in a case where EU and ES are smooth. Then the conjecture would be that they are homogeneous. And the theorem that exists is that EU, ES are smooth, and you preserve a pseudo-Riemannian metric out of nowhere, just comes from heaven. In that case, you must be homogeneous, and so that you don't exist. There's no examples that have not maximal rank and not 0 rank. So that's a Young Fong.
Fong.
What?
Fong. F-A-N-G, I think. Okay, thank you very much. Anyone else? So I think there's time for, we're supposed to stop at 9:30, so there's time for 1 or 2 more speakers.
So I guess this question will actually come up in my talk tomorrow, but I want to make a sort of easy version of the question first. I mean, the simplest possible form. It's actually a simple question. So you have just a 3-manifold with a volume form, and then you begin first, let me just take X any vector field, and suppose that this is volume preserving, right? So you have that. So this means that So therefore, this is always closed, so it gives you a class. then a quick sort of definition. You say X is null homologous. If this class is 0, so in this case you have a primitive. So in this case you have a primitive, let's say d tau, and then you sort of find the following invariant, the helicity of X. And you take the integral, you take the primitive, you apply it to the vector field, and you just integrate it over M. So this is a nice quantity. Looked at by lots of people, Arnold in particular. And so here's the question.
It doesn't depend on tau, right?
Oh, right. So there's a bunch of sort of very easy things. It doesn't depend on the primitive you pick. Here's the question. Does there exist X and also with zero helicity? So the obvious thing to try, so if you want to sort of do, so just to sort of do quickly, if you want to do this in the sort of contact case, the form would be sort of something like that. So if you contract, obviously, you get the alpha, and the helicity in this case. The volume, which is always non-zero in the contact case, right? So, yeah, so that is the question. You know, you might be wondering, do you know an example of something with zero helicity? So you might.
And if it's a suspension, what happens?
Sorry?
It's a suspension.
The suspension will never have non-zero class. It will never be non-null. It will never be null homologous. So that rules out suspensions. Yeah. So this is really kind of, you know, you want to be in this sort of realm of something close to something contact, but so maybe just one quick example so you see what could happen. And then I'll tell you briefly why. I'd like to know that. It's a very natural question, but.
So does this quantity, does it have a sign or not? Is it always a
Well, in principle, when you define it, you don't know what the sign is. So here in the contract case, you know, sometimes the sign kind of depends on the conventions that you make. So the sign is not really that relevant. I mean, it's really the vanishing or non-vanishing that I'm really interested in. That's the reason. So if you were to take, I don't know, the usual thing, PSR2R divided by gamma, and X is the geodesic vector field that we've seen many times. Well, we know what happens. But then if you do something like this, for example, X plus SV, V is just a vertical one that corresponds to the SO2 action. So it's very easy to compute that for this less than or equal to 1, this is actually an also, and then you have FS, then you have, let's say, positive helicity, but then exactly for X is equal to 1, it's like, you know, you think about the picture in the Lie algebra of this, so the X is, in the Lie algebra, sits in the hyperbolic set of the light cone, basically, in SL2R, and V is a sort of vertical, so sits inside the light cone. As you actually deform, you hit a point in which you hit the actual null cone. So for S equal to 1, it's essentially a horizontal flow. I mean, X plus V, H plus V is all the same, more or less. And for that one, you get helicity 0. So that somehow the most interesting flow with 0 helicity is a horizontal flow. And this is a sort of example of a one-parameter family of an also flows that kind of deform all the way to kind of, you know, 0 helicity.
They're all null homologous.
They are all null homologous, yeah. Very easy to check too.
It's true in variable curvature?
Sorry?
Is it true in variable curvature that the horizontal flow has zero helicity?
Well, in variable curvature, I mean, I don't know that. In variable curvature, this is just constant curvature. So it is possible that it may have.
Why is it called helicity?
The helicity, because there's well, there are people here that probably know a lot more than I do about that, but it's sort of related with sort of fluid flows. It kind of describes how much the orbits sort of curl, essentially. Yeah. The interesting thing about this, I suppose, at that quantity, and that will come out in my talk tomorrow, is that the vanishing or non-vanishing actually controls resonant forms. It has a very strong influence on the resonant forms at zero, which are relevant, for the world zeta function and so on. But I think it's I've been asking this question for 2 or 3 years now, not too long, but it sort of feels that, they say, Monday, Wednesday, Friday, I think that it should be non-zero, and then the other days of the week, I think it should be a counterexample. So this is how sure I am. There are other things you can prove. I mean, other flows where you can prove that the helicity is non-zero, but you always have to do something a little bit non-trivial once you go out of the contact case. So it would be great to kind of, either have a proof that it's always non-zero or have some example.
You said before that the sign depends on your convention, but once you fix the convention, can you provide an example with both signs?
Of an also with both sides?
I mean, like two flows, each of them have a different sign.
I think the answer is no. I mean, so you're thinking about always keeping them anosmal, right? Because otherwise, I think it's very easy. In this case, you just go for S larger than 1, and then you change the sign of the helicity. But no.
Okay.
So once you go, what happens is that once you pass 1, you get really to the inside of the cone, and they become all essentially elliptic. So you go from the hyperbolic one to sort of elliptic ones, and at the critical point, you go through a horocycle type thing. Now, I think the question you were asking, if I understood correctly, maybe whether they have maybe like a one-parameter family that. No, right? I mean, so I think the answer to your question is no, I don't know. In the not setting. Because that might be almost what I want if you want to have a counterexample, right? At least if you were in some kind of path component, path connected component.
I think the question was not about having a one-parameter family,
Yeah.
but rather like 2 examples, separate, putting in some other like separate connecting components of the space of Anderson.
Yeah, but you have to be the question to make sense. If you understand, you have to kind of fix the manifold and fix the sort of orientation and your volume.
Volume, yeah, absolutely.
So you're kind of working with this sort of all and also flows that preserve that volume form. I don't know what that's.
Is this perturbation equivalent with putting a magnetic field?
That is exactly right.
You turn on the very much. So anyone else? 5 more minutes. So you will be the last speaker, I think.
I think one is one question I asked Olympia some time ago, but it seems nobody or new people. It's about these quasi-Fuchsian groups. So you take a discrete subgroup of PSL2R, you embed it in PSL2C. It's a co-compact group of PSL2R, but convex co-compact group of PSL2C, is a natural embedding. This is the isometric group of H3. This is the isometric group of H2. So H3 is a ball. So you get the fundamental domain for the action, which is co-compact on H2. Now, if you look at the natural action on H3, you get a cylindrical manifold, which is called, which is really let's say sigma. It's a compact surface. It's a compact surface. Compact hyperbolic surface. And gamma on H3 is R times sigma. It's a metric which is dt squared plus cosinus hyperbolic of t times g sigma, which is the hyperbolic metric. And now you make a quasi-conformal deformation. Even a one-parameter family, so you get gamma t, a family of quasi-conformal deformation in PSL2C, which is really not in PSL2R. Then, so the limit set of this group here is going to be the circle here. If you perturb, it's going to be a quasi-circle.
What do you
Perturb your group, the friction group. You have a friction group, you perturb it, so you get a quasi-friction. This is a quasi-friction group, yeah?
Do you really want that it's not at all in PSL2R, or?
Yes, otherwise it's easy. I haven't asked the question, but the question will get clear. So you get a manifold with the same topology.
What did you draw? What do you draw here? You say lambda of gamma plus?
This is
subgroup?
No, gamma t, it's gamma t.
This is the limit set of the deformed group.
Maybe the t is not a good.
T is just 0 and 1.
Yeah, but I mean, because you use t for. Never mind.
Sorry, yes. That t was this coordinate here. So you get a non-compact manifold which has a convex core which is thickened. Here the convex core is just one surface embedded, totally geodesic. And now you want to understand the resonance of this. So, oh sorry. And now what are the resonance? That's the question. What can we say about the resonance?
So what you draw this
Yes,
wiggly cylinder replaces the hyperbolic cylinder you had before.
yes, so this is a kind of deformed cylinder. The metric is not a product anymore. The geodesic flow is still axiome in this case, so it's an axiome geodesic flow. So we know how to define resonance. If you compute the resonance for I probably mess up the thing, but what you can check is that the resonance are in some lines for the Fuchsian case. So at t equals 0, you get and they're completely explicit. They're given by the eigenvalues of the Laplacian on this surface. Everything is computable because it's just a product. And now, what happened when we deformed, and in particular, is it possible to show that they would lie in some bounds, like
typically like the one that Fred explained. That's not known, and I think it's a difficult problem. And it would be interesting because we don't know cases like this of axiomatic flow where we have a bond structure like this. This would be the first example as far as I know. Except it's a product. That's the first question. And you can hope it's true that in some bonds, the Weyl resonance for t close to 0, let's say. And the second question is related to the talk I'll give tomorrow. Is this thing about the market frequency. So you take a surface with a Riemannian metric. With no conjugate point. Maybe GK for J power 1, 2. So you take two metric on a surface with no conjugate point. Maybe you can assume that genus is bigger or equal to 2. And you assume that their flow, Phi G1, is smoothly conjugated to the flow of G1, of G2. Assume that this. So if they are smoothly conjugated, or G1 and G2 are isometric. And you see in what I will explain tomorrow, it may be possible to prove they have the same complex structure, but there is one missing point, which I will explain tomorrow about constructing certain invariant distribution. So that's, this is maybe a more general type of question that like Keith asked in an old paper with Katok in negative curvature. So this is what you could expect, I suppose.
But can you find two surfaces with conjugate points and smoothly conjugate geodesic points which are not isometric? Or?
With conjugate point?
I mean, where do you put the conjugate points assumption here?
So what was it? Soil surfaces, right? What was the question?
I think yes.
Zoll surfaces, but Zoll surfaces in genus 1 and 2.
Oh, right.
No, in genus 2 and
Yeah, orbit conjugated or conjugated?
Sorry?
Yeah, orbit conjugated or conjugated?
No, C infinity really conjugate.
This is time preserving.
Time preserving. Yes, time preserving conjugacy.
Maybe or C2, I don't know. Let's say C infinity. It's not an easy question.
And is it known if they have negative curvature?
Yes, in negative curvature, this was proved by Otal. And what I will explain tomorrow is it's true for if they are Anosov. Yes?
For your first question, I still do not understand why is it trivial if this group gamma S has still parts in PSL2R? I mean...
Yes, if it's in PSL2R, then...
No, but you wrote that the whole group has to move out.
Yes.
I mean,
Yes.
but if some part of the group stays in PSL2R and...
no, then you can ask a question. It's not... it's possible. I mean, I don't know then. I just know if it stays in PSL2R, because then...
Okay, yeah.
Because then it remains a product. So
That's your question.
Yes, okay, yeah, okay. Okay, you want to perturb it such that not the whole group is in PSL2R.
It would be even nice to do even numerics to see what's going on. Yeah. course, high frequency is complicated. But,
If you assume that, in general, the trap set here for the left problem, the trap set is not contained in a plane or in a smooth
no. Of course, in this case, it has a nice structure. But as long as you perturb, it's becoming complicated. And it's not.
Your X-ray has kernel. You can try, if your X-ray has a kernel, you can try to do a deformation like,
That's right. Yeah.
like it.
you still have a trap set axiome. I mean,
Yeah, it's in the axiome thing, but here it's like asking something about the optimal spectral gap.
That's probably okay. That's like sort of cylinder. That's a nice.
Even proving an explicit spectral gap is not known in this case. So the question about the gap is
Well, thank you very much. So thank you to all the speakers who. All right. So we might actually write. You want to write a document or something which collects all the
It's
questions?
just a suggestion, I mean.
Okay. So do we have all the speakers' consent if we put all the questions in the document? Okay, great. Okay, thank you very much.